So, Jason, I know that lately you have been going on a little journey of technical exploration about really using the tools that we have in the real world. And one of these was with quantum computing.
That is correct. As we've talked about this on the podcast before, we theorized that one of the ways in which quantum computing would become democratized was through the clouds. And sure enough, they all now have some form of quantum computing available to their cloud clients. And I was sent a very nice email from Amazon. I don't know how many other people received this, maybe a lot, but I received it and I read it and I responded to it, which was Amazon Braket. So for those of you who are familiar with Amazon EC2 or S3 or any of the other services Amazon has through AWS, Amazon Braket, and that's spelled B-R-A-K-E-T,
Okay.
that is their cloud quantum computing platform. And what's most important to it is the quantum simulators that are available, which means you're not programming a quantum computer, you're programming classical computers that act like a gated set of qubits that you can then perform various tasks.
Okay.
So really this podcast is about what was it like to actually fire up a quantum field, and was it useful?
Yeah.
And then the next set of questions that I want to answer is, what use does it have? Because of the fact that I think the conclusion is that the quantum computers themselves right now
Yeah.
are not terribly useful, but there's profound learnings that are coming out of mucking around the way that I did.
Okay, I think those are all great. So why don't you start us at the beginning? So you wanted to use Braket. Tell us about that.
Yeah, so my goodness, how do you start? I've never used anything like this before. So there was a lot of documentation, and wow, Amazon, I'll give them credit. I'm sure all the other clouds have as much or more documentation, but Amazon sure did a great job of putting out like a minor university course in how to actually get a quantum computer going. They want to sell their services. They're totally motivated to teaching people how to use those services.
Right.
But it was really high quality teaching. That's one thing I wanted to point out. So I did some reading.
Which you would expect, like if this is going to be one of the major new frontiers on which the public cloud, pay for compute battle is fought, then you'd think that there would be great focus and attention on doing it well
Yes.
by all the major players.
And my goodness, the one experience that I've had, which is purely anecdotal, was great.
Yeah.
Which is that's a great start. Right? It's just the learning is there. If you're a young developer or you're a student, my goodness, get in there.
Yeah.
All right. So number one, I basically wanted to create a hello world in the quantum simulator.
Sure.
Well, my goodness, did I ever learn a lot? Because you can absolutely get the letters rendered, but once you start saying to it, hey, I want to do natural things like error handling, it's like, well, there's no error handling on a quantum computer. Once you make your measurement, you have to essentially reverse out if you want to see how the thing occurred. And really what you're doing with a quantum computer is measuring statistical states of qubits. That is what programming a quantum computer means. Very, very different than a classic computer. So all of a sudden, you start to feel extremely limited because you take all this classical knowledge of, well, I know what a computer can do for me, and I know how regular computer programming works, and you just have to take all that and just throw that to the side. And I felt literally like a baby exposed to the wind in terms of knowledge, because it was like, this is a new experience. So the way that you're handheld into actually firing up a quantum field involves classical computers. Classical computers are the things that are controlling the quantum field.
Okay.
So what is the quantum computer?
Yeah.
The quantum computer is the quantum field. Okay? And so therefore classical computers are the things that are actually initiating this field and taking the measurements and that kind of stuff. So that's one of the early lessons is, wow, classical computers are deeply imbued in all quantum computing methodologies.
Sure. Okay. Yeah.
And so initiating the quantum environment is a handshake between a classical computer and and basically a quantum field.
So this was a bona fide qubits-based quantum computer you were using that you were basically you interface with a classic architectural computer and it interfaces with the quantum computer.
Correct. I had a number of choices from Amazon. Amazon, because there are many types of quantum computers.
Right.
And I just happened to be using the Atom, which was not even a conscious choice. It just was the first on the list, and I clicked it, and away I went. Obviously very different than quantum annealing. Therefore, I was setting up a gate on a qubit, right? And so therefore, it was a gated quantum computer.
Okay.
So the initiation of the quantum environment was the first piece, but then there was defining the quantum circuit, Tim. And the circuit is, the reason I think that word circuit is correct is because there's the initiation of the quantum field, there's the measurement of the qubit, where it is statistically between 0 and 1, essentially. And then basically that performance of the measurement collapses the qubit. And that's expected. So it kind of has a lifespan. Classical computers don't really have that concept. You don't have a lifespan of bits, right? You do in a quantum computer. So therefore, you have to think of it as a set of gated qubits that go through a life cycle, and that life cycle you call a circuit.
Okay.
Interesting. And so running the circuit is a whole lot easier on your quantum simulator. And so if you're going to perform a little hello world, you really want to do it on the simulator, because here's what happens. The quantum field, quite often, the statistical result of whatever it is you ask it to do won't be the same. In other words, it's probabilistic, and therefore the measurements of the qubit won't always be the same, even though you've asked it to do the exact same function.
Right.
Which means this what is becoming quite common, I'm realizing, is you actually have to do multiple shots of circuits. That I'm using the terminology that's used in doing this. So these shots allow you then to cluster a set of measurements around what is presumably the truth of what you've asked it to do.
Okay.
So let's transform this knowledge into Shor's algorithm just for a moment.
Sure.
That means that's why you need more than 4096 qubits to solve RSA 2048, because if you're having to do 1,000 shots per circuit, that's going to mean you need 1,000 qubits per piece of number space. So in really simple language, you've got to perform quantum computing many, 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 many times to perform one thing. That will improve as error handling and coherence improves. Not all qubits are created equal. Right. And that'll be another podcast we talk about at some point, because things are improving radically. But at the current state of the art right now, early 2025, I can tell you that, wow, you don't get a lot of qubits available to you. And the qubits you do get are not terribly stable and will require, for every single simple gated function, many individual life cycles to occur to statistically get to the truth.
So this suggests to me two things. One is, if you're going to be using this pragmatically to solve real problems today, they're probably going to be extremely specialized and very high value, or they're not worth solving.
Yeah, and I would say that if they're that high value, you're probably not even using a quantum computer yet. Not certainly ones that are available
Right.
democratically through cloud systems.
Or the other thing that it suggests is that this is really for people to get their feet wet and to start to figure out, this is an appetizer.
Yeah.
This is for the potential market, which, eventually we expect to be large. This is for the people who may be buyers to start to use it and figure out the use cases that they're going to ultimately have for it, so that when the time comes, they come and spend.
100%. 100%. That is what it is for. And I would say that for a person like me, it's an enormous amount of learning to start from the most, I don't know anything, completely totally humiliated down to the raw level of, I don't know how this system works, but I want to get something out of it.
Right.
And then realizing that, wow, I need to shift my brain completely in order to understand how to get something out of this. And the learnings are profound. And I wanted to make a couple points. And I have some notes here, Tim, about what other people have learned in their own words. And what we're finding is this. It turns out that classical computers that have been turned into quantum simulators are actually awesome computers.
Okay.
So in other words, yes, it's a classical computer, but the way that it's set up is to act like a gated set of qubits. And so forcing your brain into these kinds of circuit shot measurements, that style of logic, even with if it's simulated and not using actual qubits in a quantum field, it turns out that there's powerful lessons to be learned in programming because of that. Okay. And so give you some ideas here. If you are having now to patternize these multiple shots on a non-deterministic computer system, which is essentially what it is, then I find it fascinating that the mathematics behind Monte Carlo simulations on classical computers has been radically rethought recently. So in other words, the field of statistics and classical computers has looked at quantum computers and was like, wow, we have to up our game. And they did up their game. And all boats have floated up because of these new disciplines that are coming out of quantum computing.
Right.
It's fantastic. So, but that's kind of a pure mathy thing. But remember I told you, there really is no concept of error handling because you can't interrupt these quantum fields and start taking measurements because the whole thing collapses by definition, right?
Sure.
And so this reversibility concept, the probabilistic approach, resource optimization, when you have to code in such a way where error handling is not really possible, and you have to be able to somehow reverse the logic that got you to this non-deterministic event, holy smokes, you have to force yourself to optimize. And this reversing of logic technique was never muscles we ever had to develop as programmers.
Yeah.
And now we do. And now people have taken these learnings and went, hey, in my normal course of events, I can make computing systems that are now so much more energy efficient because deleting information creates heat. to make it the most basic words possible.
Right.
And so if you don't have to do these kinds of information deletions, and you can rely on reversibility as a concept in programming, wow. Like all of a sudden, the amount of battery that you burn to do X, Y, and Z is much less.
Okay.
And so that's, resource optimization, incredible. And that's coming out of, because we're forced to do these things with a quantum computer. And I would say the final one has to do with just general thinking around, all right, if I have to program gates of qubits that are very unstable for things like material science and any kind of modeling, I think that the modeling people are doing on quantum computing is really teaching everybody in the field right now that there's better ways to do things. I think that there's so many academic papers being written right now that haven't made it to industry, let's say, that are all about these forms of optimizations that have come from, wow, look at what I learned by programming a small quantum computer. I'm going to take my learnings to a classic computer, and maybe now I don't even have to have a quantum computer, is what some people are saying.
Yeah, which I think is an interesting outcome, depending on what you're doing, because we've sort of been waiting for, certain kinds of computing tasks. And it's, again, this phrase, cryptographic relevance, when are we going to get when are we going to hit a certain milestone for whatever the task is where we can do it with a quantum computer. And if you can do it with traditional architecture, you got all the chips you want, right? Like, it's just, it's a simple engineering project and largely a budget exercise at that point.
You got it.
Right?
Yep.
So that's fascinating.
Yeah, that's it. I know that's pretty in the weeds, but for those of you who are curious, I guess the bottom line is there's learning to be done by just messing with it. The public, like the cloud platforms that are out there are offering tremendous education. Soak it up.
Yeah.
Experiment. Play even just with a simulator, and you'll learn.
All right. That's fascinating.
Yep.
Jason, this has been Rukazos.
Thank you, Jim.